Hey kids, this is Mr. Cozy, and this is video 59, where we look at some applications of logarithms to solve problems that maybe we haven't thought to solve before. We are going to look at using logs to solve exponential equations, using logs in problems where we get quadratics, and then applications of logarithms. So yeah, let's get started. Remember that if we're solving an exponential equation, the trick is to get the bases to be the same so that you can drop the bases and just look at the exponents. And this works fine until we have a problem where there's just no chance of getting the bases to be the same. We have no shot here. So what do? What we do is we take a log of each side. Now, it can be common log or natural log. Either one works. But if we have an exponential problem where we can't get the bases to be the same, taking a log of each side turns this into a logarithmic problem, and I can use logarithmic properties like moving the exponent out in front. X plus 1 parenthesis times log of 5 equals log of 7. And then I can just solve for x. Divide log of 5 to the other side. Log of 7 divided by log of 5. Subtract 1. And I'm going to have my answer. Now, to get an actual number for this, I need to use a calculator, and I'll need to round because this will not work out evenly. I also need to watch parentheses. Log of 7 divided by log of 5, and notice I'm closing off parentheses on the logs, minus 1. And that's going to give me x is 0.20906 ... And I would round it to whatever place it told me to round to. Okay? So if you have an exponential equation where you can't get the bases to be the same, take a log of each side. Now if you can get the bases to be the same, it's usually easier to do that. But if you can't, a log of each side works. Okay? Let's look at a different kind of a problem. Oh, hey guys, by the way, everything that I did here works exactly the same if I used ln. This all works out the same if I use ln instead of common log. In fact, let me show you here. If I enter in this exact same equation, but using ln of 7 divided by ln of 5 minus 1, I'm going to get the same answer. Okay? Common log, natural log, doesn't matter. Okay, so this is one situation. Now, an application of this is the following. You have $5,000 invested at 7% interest, compounded, and monthly. How long will it take to accumulate $8,000? Okay? So I'm going to use my compound interest formula, which is A equals P times 1 plus N or r over n, sorry, to the nt power. The difference here from when we have used this previously is that I have a starting amount, a rate of interest. I know that I am compounding once a month, and I also have an ending amount, and I want to know how long it will take. I want to solve for t, and t is in my exponent. Okay? So how am I going to solve this? Well, first thing that I need to do, remember the order of operations. I cannot multiply this out, because in order for me to be able to multiply this out, I would have to work out this whole exponent, and I can't because there's a variable in there. So I cannot multiply this out. Instead, I have to divide the 5,000 over to the other side. So I'm going to have 8,000 over 5,000. I'm going to work out what's in these parentheses here. Oops, sorry, wrong button. There we go. 1 plus 0.07 divided by 12. That's the base of my exponent. So I'm going to round this. I'm going to go 1.0058333 to the 12t power. Okay. Now this is an exponential equation, and I have no chance to make these two bases the same. So I'm going to take a log of each side. That's going to let me move this exponent out in front. So that I'm going to have log of 8/5, because this reduces, equals 12t times log of 1.0058333 rounded. I can then divide everything that's not the t over to the other side. Log of 8/5 divided by 12 log of 1.0058333 equals t. Okay. Now, as you can imagine, when I put this in the calculator, I might want to go in baby steps. Log of 8/5 is a number divided by parenthesis, because I want to divide this whole thing. 12 log of 1.0058333. And it'll take me about 6.7 years to accumulate $8,000. Okay, so this log lets me solve exponential equations where I can't get the base to be the same, meaning all of the exponential growth and decay formulas that we learned, we can now solve for something in the exponent. We can do that because taking a log of each side lets me move the exponent out to be a normal number like everything else. Okay? All right. Let's take a look at one more example, and then we will call it a day. Log of x plus 3 plus log of x equals log of 10. Okay? Now this is just going to be a normal log equation. I've got to crunch the logs on my left side. I can then cancel the logs. The thing is that to solve this, I'm going to have to work with a quadratic. Okay, this is a quadratic. So I need to pull everything to one side and factor. Two factors of negative 10 that add up to 3, x plus 5 and x minus 2. So x is negative 5 or positive 2. One consequence of solving a log equation, especially if it's quadratic, is it's possible that one of these roots is extraneous. Because remember, I can't take the log of a negative number. If you go all the way back to when we introduced logs, you'll remember that the domain of logarithm is 0 to infinity. I can't take the log of something negative. In this original problem, I'm taking the log of x. So x cannot be anything that's negative. Therefore, I have to throw out this answer and only look at the 2. Okay? When you do log equations that turn quadratic, you've got to check your answers because you can't take the log of something negative. Now, sometimes that means that you will throw out the negative answer, but be careful. Having a negative answer isn't the problem. Taking the log of a negative number is the problem. Okay? We'll talk more about this and other things tomorrow. I think we've looked at enough for tonight. Have a great day, and I'll see you later. Bye.